In this episode, we will talk about Qwen3's technical report. We've got the technical report right here, fresh off the press, detailing the new Qwen3 family of large language models.
That's right.
Our plan today is to really unpack what makes Qwen3 different. We'll look at the architecture, how it was trained, which is quite something, and its performance.
Yeah, the results are pretty interesting.
Exactly. We want to give you a clear sense of these advancements without getting totally lost in the weeds, you know?
Makes sense.
Okay, let's get into it.
So I think one of the first things that really jumps out with Qwen3 is, well, its core design. A lot of current models, you often need different ones for different jobs, right?
Right, like one for chatting, one for complex problems.
Exactly. You might have a chat-optimized one, maybe like GPT-4o, and then maybe a separate reasoning model, something like, I don't know, QW32B, perhaps. Qwen3 tries to do something different. It brings together two modes, they call them thinking mode and non-thinking mode, into just one model.
One model, two modes. Okay.
Yeah. The thinking mode, that's for the really tricky stuff, multi-step reasoning, where the model needs to, well, think it through.
Right.
The non-thinking mode is more for quick responses, things based directly on the context, fast conversational replies.
So you wouldn't need to swap models anymore? That sounds much simpler.
Potentially, yes.
Actually.
Much more efficient.
And the report mentioned it can switch between these modes automatically, based on the prompt or something.
That's the idea. It can dynamically shift gears depending on what you ask it, or even based on these things they call chat templates, which guide the interaction style.
Like a multi-tool that just knows whether you need the screwdriver or the pliers.
That's a good way to put it. A quick fact check versus deep analysis, all from the same place.
Okay.
And building on that, there's another really neat idea, the thinking budget mechanism.
A thinking budget. What's that about?
It basically lets the user decide how much computational power, how many resources the model should spend on reasoning when it's generating a response that's during inference.
Ah, so you can control how hard it thinks.
Kinda, yeah. Think of it like giving it an allowance for thinking. If it's a simple question, maybe you give it a small budget. It answers faster, less latency.
Right.
But if it's a complex problem, you could increase the budget. Let it use more compute, spend more time reasoning it out. Hopefully get a better answer.
So you're trading off speed versus depth.
Exactly. It gives the user control over that balance, which could be really useful depending on the application.
Yeah, I can see that. Sometimes you need it fast, sometimes you need it right. Okay, that makes sense. Now, besides these modes and the budget, the report talks about making smaller models efficiently. How do they manage that?
Right, that's important too. They've essentially figured out how to take the knowledge baked into their big top-tier models and use it to drastically cut down the resources needed to build the smaller one.
Like a knowledge transfer.
Precisely. Like a master teaching an apprentice the core skills quickly. So these smaller Qwen3 models, even with fewer parameters, the numbers that store what the model learned, they still perform really competitively against other models their size, or sometimes even bigger ones.
That's huge for actually using these things, right? Not everyone has giant server farms.
Absolutely. It makes powerful AI more accessible, deployable in more places.
Okay. And speaking of accessibility, they've also really pushed on multilingual support.
Oh, definitely. That's a big jump. Qwen3 supports 119 languages and dialects.
Wow, 119. What was it before?
Qwen 2.5 supported 29. So, yeah, a massive increase.
That really opens things up globally.
It does. Better understanding, better generation across way more languages. It's key for reaching more people.
No kidding. And the models themselves, they're open access.
Yes, that's another significant point. They're all released under the Apache 2.0 license.
Which means
researchers, developers, anyone really, can access them, study them, build on them. It encourages reproducibility, community work, and potentially speeds up innovation for everyone.
Okay, so fostering an open ecosystem. That's great to see.
Definitely.
All right, so we've got the big picture. Unified modes, thinking budget, efficient scaling, multilingual, open access. Let's dive a bit deeper into the architecture itself. How are these models actually built?
Okay, so structurally, there are two main flavors. Dense models and then mixture of expert models, or MOE.
Dense and MOE. Let's start with dense.
Yeah, they have 6 dense models. They range from pretty small, 0.6 billion parameters, up to a fairly large 32 billion.
Okay, quite a range.
And the basic architecture is pretty similar to what they had in Qwen 2.5. You've got things like grouped query attention, GQA, for efficiency.
GQA, right. That speeds up attention, doesn't it?
Yeah, groups query heads to share keys and values, reduces compute, especially for generating text.
Got it.
Then there's SWIGLU, which is an activation function, rotary positional embeddings ROPE for handling word order.
Ropey, yeah, that helps with longer sequences.
Exactly. And RMS norm with pre-normalization for training stability. Standard building blocks, mostly.
Mostly standard, but any tweaks for Qwen3?
A couple of notable ones. They removed the QKV bias, a small term in the attention calculation, and they added something called QK norm, query key normalization.
QK norm. Why add that?
They say it helps make training more stable, especially for the larger models, just refinements to the process.
Okay. And context length. How much text can they handle?
All the dense models have a context length of 32,768 tokens.
32K. That's pretty substantial. Good for long documents or conversations.
Definitely. One other detail, the embeddings, how words get turned into numbers. They're tied shared between input and output in the smaller models, the 0.6B up to 4B, but not tied in the bigger ones, the 8B, 14B, and 32B. And the number of attention heads also scales with the model size, as you'd expect.
Okay, so a family of dense models scaled up with some specific tuning. Now, what about the MOE models? Mixture of experts.
Right, the MOE approach is a different way to scale things up. Qwen3 has two MOE models mentioned. One is Qwen3 30B A3B, and the big one is Qwen3 235B A22B.
235 billion parameters. That sounds massive.
It is massive in total parameters. But here's the MOE trick. Only a fraction of those parameters are actually used for any given input token. The A22B part means 22 billion parameters are activated per token.
Ah, so it's like having a huge library of experts, but you only consult a few relevant ones for each query.
Exactly that. You have a large number of specialized subnetworks, the experts, but you only route the input through a small subset of them.
How many experts do they use?
In these Qwen3 MOE models, there are 128 experts in total, and 8 get activated for each token.
8 out of 128.
Okay. And interestingly, they changed their design from Qwen 2.5 MOE. In Qwen3, there are no shared experts between layers. Each expert is distinct.
No shared expert. Does that help specialization?
Potentially. They also use something called a global batch load balancing loss during training. It's a technique to encourage the different experts to actually specialize and to ensure the workload is spread evenly among them.
Makes sense. You don't want some experts doing all the work while others sit idle.
Precisely. It optimizes the whole system.
Very clever scaling. And the tokenizer, the thing that breaks text into pieces.
They use their standard Qwen tokenizer, which is a byte-level byte pair encoding, or BBPE.
BBPE.
Yeah, it's pretty common. The vocabulary size is 151,669 tokens. Being byte level helps it handle lots of characters and languages effectively, which ties into their big multilingual push.
Right, it all connects. Okay, so sophisticated architectures, both dense and MOE, and a capable tokenizer. Let's talk training. How do you feed these beasts? The report mentions 36 trillion tokens. That's just mind-boggling.
It really is an enormous amount of data. 36 trillion tokens covering those 119 languages and dialects. It's a mix of things: high-quality web text, code, STEM material, books, reasoning tasks, multilingual data, and even synthetic data.
Synthetic data? So data they generated themselves.
Exactly. They didn't just rely on scraping the web. They used some clever techniques. For instance, they used their Qwen 2.5 VL model. The VL probably stands for vision language.
Ah, so it can read images or PDFs.
Likely, yes. They used it to pull text out of PDFs and then used the regular Qwen 2.5 to clean up that extracted text.
Okay, refining the raw extraction.
And they also used specialized models, Qwen 2.5 Math and Qwen 2.5 Coder, to generate trillions more tokens of synthetic data. Things like textbook explanations, Q&A pairs, code examples, specifically targeting those domains.
Wow, actively creating tailored training material. That's quite strategic.
Very much so. Plus, as we said, loading up on more multilingual data across those 119 languages.
It sounds like data curation was a massive undertaking. The report mentions an annotation system.
Yeah, with that much data, quality control is key. They developed a system to annotate over 30 trillion tokens.
Annotate how?
Across different dimensions like educational value, the subject area or domain, even safety aspects. These details labels let them filter the data much more effectively and mix it just right during training.
So not just throwing data at it, but carefully selecting and weighting it.
And they did this optimization at the instance level. Based on these labels, not just grouping by broad categories, they figured out the best mix using experiments on smaller models first.
Super fine-grained control. Okay. And the actual pre-training process happened in stages. 3 stages, I think.
Correct. The 3-stage process. Stage 1 was the general stage.
Laying the foundation.
Exactly. Training on over 30 trillion tokens, sequence length of 4,096. The goal here was basic language skills, world knowledge across all 119 languages, getting the fundamentals down.
Makes sense, stage 2.
Stage 2 was the reasoning stage.
Yeah.
They shifted the data mix here, focusing more on higher quality tokens, STEM, code, reasoning problems, and that synthetic data we talked about.
Sharpening the thinking skills.
Pretty much. Still using a 4,096 sequence length, but on about 5 trillion tokens of this more specialized data. They also tweaked the training, use a faster decay for the learning rate to help refine performance on these tasks.
Okay. And the final stage.
Stage 3, long context stage. This was all about enabling that long 32K context window.
Stretching its attention span.
Right. Training on hundreds of billions more tokens, but now with sequences up to 32,768 tokens long. The data mix here was mostly long texts, 16K to 32K tokens, with some shorter ones mixed in.
And technically, how did they achieve that long context?
They made a few adjustments. They increased the base frequency for the ropey embeddings using a technique called ABF. And they brought in yarn, yet another rope extension, and something called dual chunk attention, DCA.
Yarn and DCA.
Yeah, these techniques together effectively allow the model to handle sequences 4 times longer during inference than what it was strictly trained on. So it boosts the usable context length significantly.
Very clever. So a structured, multi-stage process, carefully curated data. They also mention scaling laws. Sounds complex.
It means they figured out formulas to predict the best training settings, like learning rate, batch size for different model sizes, and different training stages.
So they didn't just guess the settings.
Nope. Based on lots of experiments, they built these predictive models. It helps optimize the training for each specific model, whether it's dense or MOE, big or small, making the whole process more efficient and effective.
Data-driven training optimization. Okay, so after all that pre-training, how did the base models actually perform? They tested them, right?
Yeah, extensively, on 15 different benchmarks covering everything: general knowledge, reasoning, math, STEM, coding, multilingual stuff.
And the results, what stood out?
Several key things. First, the big flagship MOE model, the Qwen3 235B A22B base. It generally outperformed other top open source models, like DeepSeek V3 base or Llama 4 Maverick base, often with fewer parameters being activated.
So top performance and efficiency.
Right. Second, the Qwen3 MOE models in general were very efficient. They got similar performance to their dense counterparts, using only about 1/5 of the activated parameters. Big savings potential for training and inference costs.
Impressive efficiency gain.
Definitely. And they significantly beat their older Qwen 2.5 MOE models too. Third, the Qwen3 dense models also showed strong performance, comparable or better than the Qwen 2.5 versions, especially shining in STEM, coding, and reasoning.
So clear improvements across the board compared to their previous generation and other open models.
Pretty much, yeah. The tree training seemed very effective.
But pre-training is just step 1, isn't it? You still need to fine-tune them for actual use.
Yeah.
What about the post-training alignment?
Crucial step. You take that powerful but raw base model and align it to be helpful, follow instructions, and, in Qwen3's case, handle those thinking modes. They had 2 main goals here.
Which were?
One was thinking control, getting that thinking on thinking mode switching, and the budget mechanism working smoothly. The other was strong to weak distillation, basically using their best, strongest models to teach the smaller, weaker models how to perform better during this alignment phase.
Knowledge transfer again, but for the fine-tuning stage.
Exactly, making the smaller models punch above their weight.
The report outlines a 4-stage process for aligning the flagship models. Can you walk us through that? Sounds involved.
It is quite detailed. Stage 1 is long chain of thought cold start, or cold tooth part.
Chain of thought. Getting it to show its work.
Pretty much. Training it on problems with detailed, step-by-step solutions, building that foundational reasoning ability, making it explicit.
Okay, step 1. Learn to reason step by step.
Stage 2 is reasoning reinforcement learning, or reasoning RL. Here, they use harder problems in reinforcement learning, specifically GRPO, gradient ratio policy optimization, to really push its reasoning performance, especially in math and code.
Refining the reasoning with RL.
Yeah.
Got it. Stage 3.
Is stage 3, thinking mode fusion. This is where they bring the non-thinking mode into the picture. They train the model on a mix of data, some with explicit reasoning steps, some without, and design those chat templates to let it switch modes appropriately.
Fusing the 2 modes together makes sense. And stage 4.
Stage 4 is general RL. This is about broad, improvement instruction following, sticking to formats, safety, using tools, agent skills, handling things like retrieval augmented generation, or RGE. They use a complex reward system to tune all these aspects.
So a final polish across a wide range of abilities, that's quite a process for the big models.
Very thorough.
And for the smaller lightweight models, you mentioned that strong to weak distillation. How does that work?
Right. For the dense models up to 14B and the smaller 30B MOE model, he used a two-phase distillation. Phase 1 is off-policy distillation.
Off policy.
It means they train the smaller student models using the outputs generated by the bigger teacher models, like the 32B or the 235B. The student learns by imitating the teacher's answers in both thinking and non-thinking modes.
Okay, learning from the teacher's results. Phase 2.
Phase 2 is on-policy distillation. Here, the student model generates its own response first. Then, they compare the student's internal prediction, the logits, basically its confidence scores for the next word, with the teacher's logics for the same prompt. They use KL divergence, a statistical measure, to push the student's internal thinking to be more like the teacher's internal thinking, not just matching the final output.
Wow, so it's learning the teacher's reasoning process, not just the answer. That sounds powerful.
It's a very effective way to transfer deeper knowledge, yes.
So after all this complex alignment, how did they check if it worked? How did the final models perform?
Again, comprehensive benchmarks. They tested both thinking and non-thinking modes across general tasks, alignment benchmarks like IFEVL, math, HAME, coding, live code bench, multilingual tasks, multi-F, including, and more.
And the verdicts?
Very positive overall. The flagship Qwen3 235B A22B showed state-of-the-art results among open models and was competitive even with top closed-source ones.
Really? Competing with the big proprietary models?
In many areas, yes. The dense flagship, Qwen3 32B, also performed very well, beating their previous reasoning models. And crucially, those lightweight models trained with distillation.
Yeah. How did they do?
They consistently outperformed other open models of similar or even larger sizes. That really validates the strong to weak distillation approach. It works.
That's great news for accessible AI. So the distillation really paid off. Did they highlight any other specific findings from the post-training, like that thinking budget?
Yes, they confirmed the thinking budget works as intended. Increasing the budget consistently improved performance on reasoning-heavy tasks like math and coding so that user control is meaningful.
Good to know it's not just a gimmick.
Definitely not. They also found that on-policy distillation was incredibly efficient. It gave much better results than just using reinforcement learning directly on the small models, and it only took about 1/10 of the GPU time.
Wow, huge efficiency win there, too.
It's massive. And they confirmed that the thinking mode fusion stage did successfully integrate the two modes, and the general RL stage further boosted overall capabilities, instruction following, and agent skills.
Any downsides? Trade-offs?
They did mention some slight trade-offs. For the flagship dense model, boosting its general abilities through general RL might have slightly reduced its peak performance on some very specialized reasoning tasks, but it made the model more versatile overall.
A common trade-off, optimizing for breadth versus niche depth. Okay.
Seems like it.
All right. So wrapping this deep dive up, what are the main takeaways from the Qwen3 report? What's the big picture here?
Well, Qwen3 really does look like a significant step forward. That integration of thinking and non-thinking modes, plus the thinking budget, that's quite unique and offers real user control.
Yeah, that stands out.
The efficiency gains, both in building smaller models via distillation and the performance of the MOE models, are impressive. And the huge expansion in language support makes it much more globally relevant.
And the open access factor.
Absolutely. Strong performance across the board, validated by benchmarks, and released openly under Apache 2.0. It really pushes the open source envelope.
It definitely feels like open source models are rapidly catching up, offering features like this thinking budget that give users new kinds of control. The few directions mentioned, like scaling data further, longer context, better agents, it's clear they're not stopping here.
No, the pace is incredible.
This look at the Qwen3 report really highlights how fast things are moving. It kind of leaves you wondering, doesn't it? How are these kinds of advancements, this blend of power, control, and accessibility, going to change how we all work with information and technology day to day?
That's the big question, isn't it? It's going to be fascinating to watch.